2 engines, 2 rotors, 1 aircraft that flies like a helicopter and crashes like an airplane. That combination has killed more crews than enemy fire ever did. The V-22 Osprey was built to solve a real battlefield problem. Helicopters or slow airplanes cannot land vertically. Tiltrotters promise both. In theory, the Osprey takes off, vertically transitions to airplane mode, cruises at turboprop speed, lands in confined zones. In reality, the design forces aerodynamic compromises that stack risk. Start with rotor physics. The Osprey uses proprotos, optimized for airplane cruise, not helicopter hover. This reduces disk loading efficiency, hover margins, shrink power, required spikes during hot and high operations. Single engine failure in hover becomes critical. Both rotors are mechanically linked, but available power drops below recovery threshold. Descent becomes unrecoverable in some weight and density altitude conditions. This is not theoretical. Multiple fatal crashes followed power loss in hover. Now transition mode. The most dangerous phase is nacelle rotation between helicopter mode and airplane mode. Lift comes from neither system. Efficiently, rotor wash interacts with wing downwash. Control authority weakens. Sink rate spikes rapidly if one engine surges or flames out during this window. Asymmetric thrust induces roll faster than pilots can counter. Altitude margins disappear. This flight regime exists only because tiltrotters exist. Autorotation helicopters survive engine failure by autorotation. The Osprey cannot rotor. Inertia is too low. Disk loading is too high. Descent rates exceed survivable limits. Loss of power equals crash, not emergency landing crash. This single limitation places the aircraft in a higher fatality risk category than conventional helicopters. Vortex ring state. The Osprey enters vortex ring state more aggressively than helicopters. Large proprotors generate turbulent recirculation zones. Descent through downwash produces rapid lift collapse. Recovery requires altitude the aircraft often does not have during shipboard or confined landings. Several crashes followed this exact aerodynamic mechanism. Flight control, complexity. The Osprey relies on fly-by-wire to maintain stability. Mechanical linkage alone cannot control nacelle transitions. Software errors have triggered uncontrolled descents. Sensor disagreement has caused flight computers to issue incorrect control laws. A helicopter can be flown manually. The Osprey cannot. System failure equals loss of aircraft maintenance burden. The tiltrotter drivetrain includes cross-shafting, interconnect gearboxes, tilt actuators, and wingtip gear. Component count exceeds helicopter norms. Failure points multiply. Mean time between failures drops. Field maintenance errors. Increased risk. Logistics footprint expands. Sortie reliability decreases. Operational consequences. Marine Corps missions place the Osprey in hot, high, dusty, confined zones. Exactly where its hover margins collapse faucet. Exactly where vortex ring entry probability increases. Exactly where single engine power loss becomes unrecoverable. Crash record. The Osprey has suffered fatal accidents across training, combat, and shipboard operations. Most causes traced to aerodynamic transition, instability, power loss, or software-driven control law errors. Not enemy fire. The aircraft kills crews through physics, not tactics. Why it still flies? It delivers unmatched speed, range, and payload in vertical assault. It outpaces helicopters by hundreds of kilometers. It outruns many surface threats. It expands operational reach, but survivability is traded for performance. Conclusion. V-22 Osprey is dangerous because it violates helicopter safety margins without gaining airplane safety margins. It cannot authoritate it. Its minimal power loss tolerance in hover. It enters unstable aerodynamic regimes during transition. It depends on software to remain controllable. The aircraft is not unsafe by accident, it is unsafe by architecture.